In this chapter of Flying Through Time, we investigate the evolution of the shape of planes. The prime image most of us have of a craft that flies successfully is a form that comprises a fuselage, tail assembly, and a set of wings. However, this is not the only profile that can take to the skies and soar as gracefully and indeed higher and faster than the very animal that first inspired flight, the bird. Over the years, designers have created flying examples of craft that have done away with all the features that we would consider crucial to flight. Planes without tails, planes without a fuselage, and planes without even the most fundamental aspect of flight, wings. Flight has always been about inspiration. However, the early inventors had very little knowledge or information regarding the technicalities or constitution of flight. The evolution process started with trial and error. The early pioneers simply built things that they thought should fly. The contraptions that showed promise were further refined, and the failures often destroyed themselves and the pilot. Designers were at times lost for direction, as things that shouldn't have flown actually did, and other craft that should have flown didn't. Things began to move much faster when science started to define the qualities and characteristics of air and lift. However, the principle of trial and error, or build and crash, was dominant until the middle of the Second World War. After the war, great strides had been made in the arena of flight, and to a certain degree, a designer could build an aircraft that he knew would fly. But at this time, the Cold War had begun and the race was on to build very advanced aircraft, and again test planes and prototypes often fell from the sky. Even one of the most successful planes in history, the Jumbo, was built with a certain amount of build it and see. In fact, the very first Jumbo was overweight by a very large margin, and the original engines weren't powerful enough for the extra weight. Airlines that had ordered Jumbos had to wait for a new engine that was capable of getting the Jumbo into service. Today, the manufacturers of planes can build a craft with a very accurate outcome. Graphic models can be placed in virtual conditions and their performance evaluated. Today, manufacturers can even build simulators that test pilots use to familiarize themselves with the prototype before it's even finished. The test pilots of one of the latest jet fighters, the Lockheed Martin JSF-35, recently commented on how accurate the simulator was when compared to the prototype. In time, designers were able to build planes of varying shapes for very specific jobs. The Guppy is a classic example of this. The Guppies were designed for the single job of transporting the Apollo rocket stages from California to Florida. Apart from flying the rockets, the only other option was a slow boat through the Panama Canal. The Guppies cut months out of the Apollo schedules, and without them a moon landing in 1969 would not have been remotely possible. The Guppy was basically a recycled Stratocruiser. Stratocruiser was already a great package, as it was the last piston-engine commercial passenger plane. The Guppies have a most interesting way of being loaded. They're actually split in two, The cargo is then brought on and the two sections of the aircraft are rejoined. A later version of this craft was called the Super Guppy. The cargo section diameter was increased from the pregnant Guppy's 19 feet to 25 feet, and the fuselage was also stretched by 26 feet. The splitting of the plane's hull was a major operation and was only suitable for the transportation of specific items such as booster rockets. The plane manufacturer Airbus also used the Super Guppies to transport plane components from various factories to the final assembly plants. With the rapid growth of Airbus, the Guppies eventually arrived at the limit of their capacity. The planes were aging and consequently maintenance costs were rising. So Airbus decided to construct a new and better plane, and this is what they built, the Beluga. It has a main deck cargo volume greater than the Lockheed Galaxy, the Antonov AN-124, and the American C-17 military cargo planes. The Beluga carries freight over a range of 1,000 miles. In February this year, a Beluga accomplished the longest charter flight ever, 25 hours of flying including stops. The journey took the Beluga from Marseille, France, to the Aviation Air Show in Melbourne, Australia. Its mission was to transport 3 helicopters for Eurocopter. The white whales transport cockpits, fuselage sections, wings and tail units to the final assembly centres of the Airbus in Hamburg and Toulouse. Airbus is the only aircraft manufacturer to use air transport as the main link in its production cycle. At current levels of production, the fleet is performing more than 40 ferry flights a week between Airbus sites. Some of the parts that are flown by the Beluga include the 42-ton wing parts of the A330-340 wide bodies and the rear fuselage section of the A300-600 airline version. This section size is 15 feet in diameter and 72 feet long. Beluga carries these massive units in one complete piece. In order to achieve the necessary freight volume, the upper fuselage of a standard Airbus was severed at floor height and replaced by the characteristic and bulkier horseshoe structure. In order to make the loading and unloading as simple as possible, the cockpit was placed below floor level. The plane's giant loading hatch is 56 feet high when open, or about the same height as a 5-story building. The diameter of the fuselage that can be used for cargo is 24 feet and the floor width is 18 feet. The length of the freight space is 124 feet. To improve the Beluga's stability around the pitch and yaw axis, the horizontal tail was strengthened and the vertical tail was placed higher than on a conventional aircraft. Stabilizers were added to the tail unit to improve the rudder's effectiveness. Compared with the Super Guppies, the A300-600 ST Beluga offers an increase of around 30% in cargo volume and double the payload of 24.1 tons to 45.5 tons. On average, it took a Guppy 54 hours to transport the bigger components. The Beluga manages the same task in just 19 hours. The Beluga's economical service saves Airbus about 2/3 in transport costs. An early aviation pioneer spent more than 3 decades developing this radical-looking craft, the flying wing. Jack Northrop was convinced that a craft that had no turbulence from a fuselage and was designed in a manner that the whole aircraft's surface area supplied lift would revolutionise air travel. His dream was to see the skies filled with economical flying wings. Surprisingly, Northrop was not a pilot. During December 1941, Northrop provided a public test flight of a flying wing. The American Defence Force immediately saw merit in Northrop's design and concepts, and in 1942 granted him a contract to build the next prototype, the XB-35. The contract required a flying wing with a range of 6,000 miles and a top speed of 450 miles per hour. The operational height was to be 45,000 feet. On June 25, 1946, 3 years late and massively over budget, the first XB-35 was prepared for its test flights. Problems were occurring. Northrop's own company didn't have the space required to construct the plane, so he relied on assistance from the Martin Company. It's possible that this action caused production problems. Mechanical troubles were also evident with the pushing-styled counter-rotating propellers and drive system. The drive shaft had vibrations and the prop feathering mechanism was not performing satisfactorily. However, the jet age had dawned, so the decision was made to transform the XB-35 into the XB-49 jet-powered flying wing. The XB-35 used 4 Pratt & Whitney R4360 engines, and these were replaced by an incredible 8 Allison J35 turbojets. The air dams were built into the leading edges of the wings. This arrangement looked impressive and sounded impressive, but it had shortcomings. Such engines required vast amounts of fuel, so some bomb bay area was redesigned into fuel-carrying compartments or tanks. This caused a twofold problem. The range of the aircraft was now far less than the contract agreement of 6,000 miles, and the bomb bay was not able to carry the larger conventional munitions. Some argue that the final blow to the flying wing was that in the jet form, the craft was not capable of delivering an atomic weapon. As a pure bomber, the Defense Department became uninterested. The flying wing had pitch and yaw problems, which made it an inaccurate delivery platform, and it was very slow to settle from bomb release. There was one last hope for the flying wing. The US Air Force ordered 30 wings in a reconnaissance variant, the XRB-49. The XRB-49 lost 4 engines to accommodate more fuel. However, Convair was steadily making good headway with their more conventional B-36. Convair's effort was showing up the radical XRB, which suffered short range, low ceiling, and very limited bomb loads. By 1950, President Truman was making significant budget cuts. When faced with pouring money into the B-36 or the unproven XRB, he chose convention. Sometimes an idea is ahead of its time. The technology is just not there to be able to achieve the desired result. The flying wing could be classed as such. Just about all the problems of the wing could have been overcome today. In fact, they have been. But the wing did something exceptional that went very unnoticed for some time. The wing had stealth capability. It suggested that during flight tests of the wings, technicians were often frustrated because the tracking radar frequently went on the blink, and they often lost the flying wing from radar visual. Apparently, such incident reports were filed away and forgotten. Or were they? Interestingly, the B-2 was developed and built by Jack Northrop's old company. However, Jack Northrop was not one of the few that had security clearance for knowledge regarding the top-secret B-2. The blending of low observable technologies with high aerodynamic efficiency and large payload gives the B-2 important advantages over existing bombers. Its unrefueled range is surprisingly similar to the initial contract given to Northrop during the early wing development, approximately 6,000 miles. The B-2's low visibility is achieved from a combination of reduced infrared, acoustic, electromagnetic, visual and radar signatures. Even the most sophisticated defense systems find it impossible to detect, let alone track or target a B-2. Many aspects of the low observability process remain classified. However, the B-2's composite materials, special coatings and flying wing design all contribute to its stealth. B-2s in a conventional role and operating from the Whiteman Air Force Base in Garcia and the Pacific island of Guam can cover the entire world with just one refueling. In retrospect, one would have to wonder how much of Jack Northrop's research was pulled from the filing cabinet and reviewed when engineers began work on the B-2. Northrop's flying wing was overcome by the conventional B-36. However, being a conventional bomber, it had conventional problems. Bombers were slow and made easy targets for fighters or interceptors. Since the Second World War, bombers have required fighter escort, and the B-36 was no exception. Bomber ranges had increased, and the logistics of maintaining fighter escorts with bombers was a problem that stealth overcame by not needing escorts at all, as they had a cloak of invisibility. An experimental plane was the Goblin. It was designed to fit into a bomb bay and be carried with a bomber squadron. Should adversarial fighters intercept the raid, the Goblin was to be launched to engage the enemy. The plane wasn't designed to land. It had a hook-type apparatus which allowed it to be reunited with the mother plane. The plane was only 15 feet long. Its wingspan was 21 feet, and when the wings were folded to fit into the 16 feet bomb bay, the wingspan was reduced to just over 5 feet. Any dogfight would have to be of short duration, as the Goblin only carried about 130 gallons of fuel, which was enough for 30 minutes of flight. A Westinghouse jet with 3,000 pounds of thrust was the driving force for this most tiny fighter. The Goblin's first flight was on the 23rd of August 1948. The B-36 was still to come off the production line, so a modified B-29 was used for the test flight. The B-29 couldn't fully accept the Goblin into its bomb bay, as would the new B-36. The release procedure was difficult and reasonably slow. The Goblin was lowered from the mother plane and simply hung there until it became stable. It then free fell away and commenced flight. The most difficult part was getting the tiny Goblin back inside the B-29. Even today, in-flight refueling is considered a tricky manoeuvre. The tiny size of the Goblin made it very unstable in the buffeting of the B-29 and extremely difficult to get the hook onto the lifting apparatus. A mistake here could bring both planes down. In this instance, the pilot tried to hook up with speed to keep the Goblin stable. The crash broke the canopy and the pilot had to make an emergency landing. The pilot survived and the Goblin was repaired. In October, the test resumed, and this time it was more successful. However, the concept of the Goblin was never really pursued much further. The development of varying shapes of aircraft is perhaps one of the most interesting areas of the history of flight. It is this aspect of flight that has designers and engineers pushing the limits of the day's technology. Even failures are most often considered successes, as something new is always learned from the experiment process. That concludes another episode of Flying Through Time. Join us again when we further delve into our short but colourful history of flight.